In this video, we're going to talk about moments, which is a force that causes a rotation of an object. And specifically in trusses, having a rotating bridge is probably not a super great idea. Now, as we're designing these trusses and doing calculations on them, one important thing to keep in mind is something we call static equilibrium. And what that represents is the idea that our bridge needs to be stable. Static means it's not moving. Equilibrium gives us a sense that the forces acting on our object are equal. Now, in order to have static equilibrium, we need three things to happen. Number one is we need to make sure that all of our moments are balanced. So any forces that are going to cause a rotation in your truss need to eventually equal out so that we don't have a rotating bridge. Number two is all of the forces in a horizontal direction need to equal out. So if we have any reaction forces, perhaps we have a lot of wind that's going in the X direction, those need to be balanced together as well. And third, we need the Y forces. So those forces that are vertical also need to even out. So if we can make sure that our moments are balanced, our X forces are balanced, and our Y forces are balanced, we know that our bridge is in a state of static equilibrium, and we can get going from there. So we're going to dive into moments for this video, and we'll get into the X and Y forces later on.
Now, we've talked about moments before in simple machines, but we're going to do a deep dive into what it is and how that is going to affect our trusses. So when we talk about a moment is produced essentially by a force that causes a rotation. So moment and force are two different things. A moment is kind of that turning and that rotational effect of a force on an object. So let's say we have a wrench hanging out right there attached to a bolt, and we're going to apply a force to it. So that force is going to cause a rotation. That is what we consider a moment. Now for our formula, a moment is equal to d times F, where your F represents the force being applied to your object, and your d represents the perpendicular distance from your fulcrum. And that perpendicular distance part is going to be really, really, really important, because there's a few ways that we're going to measure things, especially when we have two dimensions. So we have our force that goes in our y direction. So the distance from our force to our pivot is going to be whatever that lever arm distance. If we look at a force that is horizontal and we kind of follow all the way through, that does not produce a moment at all. And if you think about it, if I were to push this direction on my wrench, that's not going to unscrew anything, right? So we need to make sure that our forces are perpendicular so that it actually produces a rotation. Now, when we're using units for moments, we can use our SI system, we can use our English customary, it doesn't matter, but it's really important that you keep them separate from each other. So in our system, our force is measured in pounds, and our distance is measured in feet, which means the unit for moment is going to be in foot-pounds or pound-foots, either way. In the SI system, we use newtons to represent force or to measure force, and meters to represent distance to get Newton meters. So it's important if you have inches, if you have centimeters, we always need to convert to that base unit for moments. Now, as far as direction goes, in the y direction, we've already talked about how up is positive and down is negative. We talked about how in the x direction, right is positive and left is negative. In terms of moments, the direction of your rotation determines if it's a positive or a negative moment. So if you have a force that causes a counterclockwise rotation, we are considering that to be positive. So if we have a force that provides a clockwise rotation, that is considered a negative force. And that's going to be huge when we get to our external and our internal forces for our truss solves. Now, the second way of solving for that is what we call the right-hand rule. And personally, I don't use the right-hand rule, but if this helps you think about your positive and your negative moment, then go for it. So what we're going to do is we are going to curl our fingers to match the direction of the rotation. So that if your thumb is pointing up or towards you, that is a positive moment. If it's pointing down or away from you, that is a negative moment. So if we have a counterclockwise rotation, if we curl our fingers in the direction of that moment, our thumb is pointing up, which means we have a positive moment. So if we use the right hand rule, we're going to use our fingers to kind of curl downward, which forces our thumb to point toward us, which means we have a positive moment, or you can just think of it as a counterclockwise motion means a positive moment. On the flip side, if we use our fingers and kind of follow that rotation around, our thumb is naturally pointing away from us, which means we have a negative moment. Or again, we could just remember that clockwise is negative. Whichever one works the best for you. So let's dig into those calculations. So we have a wrench here, and we are going to provide a force of 20 pounds. And we have a lever arm with a distance of 9 inches. So when we're setting up our equation, we know that to calculate moment, we need the perpendicular distance times the force. And in this case, it's nice and easy, right? We just plop things in. We can figure out, is it positive or negative, since it provides a clockwise rotation. So if I were to push on my lever arm, it's going to go in the clockwise direction. I know that we have to have a negative value. I'm going to change my inches into feet. So overall, the moment is going to be a negative 15 pound-foot moment, because we have an overall magnitude of 15 pound-foots for the moment, and negative because we're going in the clockwise direction. Now that one's pretty darn straightforward. Let's get into some weirder wrenches. Let's go to an L-shaped wrench. I don't know. Now it gets a little bit more complicated when we're talking about perpendicular distance, because if we follow the plane and the direction of our force, it's not 1 foot, which is a weird thing to think about because the distance is going to be perpendicular from our force. So if I were to kind of draw a line all the way out, I would have to measure that distance right there, which is going to be 3 inches from what we are provided. So if I push to the right with that force, that's going to cause a clockwise rotation, a negative moment. So I change my 3 inches into feet. If I dig into my moment calculations, we find it's a negative 5 pound-foot moment rotation. Now let's get a little bit weirder. Let's go to a Z-shaped wrench. Now we have to make some decisions for our perpendicular distance. So if I follow the direction of my force all the way down to kind of this spot, I need to know this distance right here. Not this distance, because that is parallel to my force. I need to find that 90-degree angle. So I need the distance of this plus the distance of this for my moment calculation. So we're given that info right off the bat. We're given that 9 inches usually to mess us up. But I'm looking for that perpendicular distance. So I need 18 inches, which I'm going to convert into feet. Then I can use my moment equation, my perpendicular distance times my force. And because that's going to cause a clockwise rotation, that's going to be a negative value. Okay, so that's kind of our moment basics. Let's talk about how we're actually going to use that for truss solves. Now, we talked earlier about static equilibrium, where our moments are balanced, our forces in the X, our forces in the Y are balanced. So we need to figure out how much force or maybe how much distance is required to make sure that my moments on an object are nice and balanced. So again, for moments, we need to make sure that the moments that are going clockwise are equal to the moments that are going counterclockwise, so that the sum of all of those moments in relation to a fulcrum are 0. So if we add up all of our moments, they need to equal out to be 0. So let's talk about an example. Let's say, let's go with an easy one like a seesaw. So we have a fulcrum hanging out there in the middle. And we've got a couple of teddy bears, aw. And our goal is we want to make this nice and balanced. But if we have a bigger object, more force, we need to manipulate the distance in order to make sure that everything is nice and balanced. So I'm going to replace those teddy bears with the force that they provide going down. And my overall goal is I want to figure out how far away do I need to put that fat old teddy bear so that everything is nice and balanced. So I'm in static equilibrium. So I'm going to start with that static equilibrium idea where all of our moments added together are equal to 0. And I'm going to find the moment of each of those and kind of set up my equation. So I know that if I add the moment from force 1 plus the moment of force 2 is going to be equal to 0. But I need to figure out which one is positive, which one is negative. So if I look in terms of my fulcrum, my little teddy bear is going to be pushing down this way. So if that was the only force, that would cause a counterclockwise rotation. So that is a positive moment for M1. And for M2, that is going to provide a negative moment because that is in the clockwise direction. So I'm going to change my equation just a little tiny bit to show that. So if I have M1 minus M2, if I add that over to the other side, everything is nice and positive. I'm going to break that down. My moment 1 is going to be distance 1 times force 1, which is equal to moment 2, which is distance 2 times force 2. And then we're going to plug those numbers in and try to solve. So we know both of our forces, 25 and 40. And we know our distance for that first one. We're trying to solve for that, that second distance. So if we isolate, divide everything by 40, we come up with an overall distance of 2.5 feet. So that means we need to put that fat old bear 2.5 feet away from the fulcrum. So then our next task is we need to use this for truss calculations. So now we have some different directions going on. So let's talk about how to solve that for trusses.
Now, a seesaw is a great example of moments in essentially one dimension. But what happens when we have forces in the x direction and the y direction, and we don't really have a fulcrum to base our calculations off of? So in the seesaw, we have that nice little fulcrum smack dab in the middle, but that's not really the case for the truss because it looks like in our case, we have a pin joint right here based on the x and the y reaction forces happening on joint A. And it looks like we have a roller over on the other side because of that vertical reaction force. So let's say we wanted to find the magnitude of our dy. We want to see how much force is required there to make sure our truss is in static equilibrium. When we're dealing with trusses, the first thing you want to do for moments is you need to select a fulcrum. The seesaw had a fulcrum that was available to you to take your measurements off of, but for this, we need to select a fulcrum. And what I would do is I would pick a point where you eliminate a lot of your unknowns. So if we think about it, I could select that middle point to be my fulcrum, and we would have a positive moment from our dy. We'd have a negative moment from our ay. But that means we have two unknowns in our equation, so that's probably not a good idea. So what I recommend is I'm going to select a pivot point where I kind of eliminate a couple of things, because if you think about moments, it's a force times a distance. If my fulcrum is right here, my distance for RAX and RAY is going to be 0 for both of those. So we kind of get rid of those automatically. So I'm going to imagine that my fulcrum is right there to make my life easier. And I'm going to base all my calculations off of that. So let's see how that works. So if this is my fulcrum, I'm going to think about, let's start with joint B up at the top. So we have a 25-pound force that's going this way. So what I need to do, if this is my rotation point, think about if my 25 pounds are pushing this way, which way is this thing going to rotate? And it looks like it's going to rotate my bridge counterclockwise, which would be a positive moment. So I'm going to say MB, and I'm going to keep that as positive value. If I look at joint C from my fulcrum that I chose, if I had a downward force, that's going to go clockwise, so I'm going to call that a negative moment. And for RDY, same idea. If that were to push straight up, that's going to go in a counterclockwise motion, which must mean that is positive. So I'm going to say MDY. And in order to be in static equilibrium, remember, those have to be zero, which means those are essentially going to balance each other out. Now, I'm not 100% sure that RDY is going to be going upwards, but at the end, my calculations will tell me if it's a positive or a negative value. So let's start breaking this down. For joint B, my moment is force times distance, so I have a force of 25. I'm going to scooch it over here. Now let's think about my distance. If I were to continue that force all the way over here, from my fulcrum, my distance would be from my pivot up to my meter stick right there, which in our case is going to be 8 feet. So I'm going to say 25 times 8. Now for joint C, I have a force of 200 pounds, and I have a distance of 10 feet, because that is my perpendicular distance. For the moment around RDY, my force is RDY, which is that reaction force, and the distance away looks like is 18. If I kind of follow that, it's going to be 18 feet away. And that all needs to balance out and equal 0. So from there, we can kind of just do some math to try to solve for our unknown. So if we have, 25 times 8, we have, what is that, 200? Minus 200 times 10 is going to be 2,000. Plus RDY times 18, and it looks like I'm running out of room a little bit here. So if I combine those, I get negative 1,800 plus RDY times 18. So if I add my 1,800 over to the other side and divide by 18, I find that RDY is going to be 1,000 pounds. And that number came out positive, so I know I'm on the right track as far as my direction goes. So again, when thinking about moments, which is that cause of a rotation, think about your force times your perpendicular distance. In terms of a truss, because we're not given a fulcrum, you need to select a point, and I would always pick a point that eliminates the most reaction forces.